Um, Chapter 15 was about water. Chapter 16, I guess chapter 15 is about qualitative stuff, solubility, and the like. It builds on the precipitation stuff that we've done. Chapter 16 is about solutions. Um, it's about making solutions, it's about concentrations, it's about diluting solutions, and things like that. So, still three. No, Caitlin shows up. We'll catch her up. So we talked about solute being what is being dissolved. Solvent is the thing that does dissolving. In science and in generally life, we're concerned about how much of something is there. If you have a pool, um, hopefully somebody goes and checks the pH, which tells how acidic or basic it is. You have chlorine levels. You have different levels that you have the test strips that you dip and you check and all of that because you want the concentrations to be right. Because if there's too much chlorine, your eyes will start to get red. If there's too little chlorine, things will start to grow. Um, if you own a house, you're concerned with, especially if there's well water, how much stuff is coming out of the ground in terms of different elements, ions. Our water in our area is relatively high in iron. It's not that bad. It wasn't, oh my gosh, you need to put something in to filter it so you can drink it, but it's probably a little higher than it should be. So there's all sorts of applications to this, and we'll briefly talk about some things. Um, we want to know, like, we have the properties, polar, nonpolar, whatever, determines how much will dissolve or whether something will dissolve. But when you're actually dissolving things, there's three things that will make something dissolve faster. Oh, there we go. Most of the time we say stirred. If you put Kool-Aid in water, you stir it up to help it dissolve faster. Really, the better word is agitated because you can shake things and help them dissolve. You can wash them, swirl them back and forth. So you stir something. The particles are made. This is where, if we were at school, I would take a sugar cube and a teaspoon of sugar and put them in water, and we would see which one dissolves faster. The sugar granules, because you have all sorts of tiny little faces on each of the pieces of sugar, you have a much larger surface area. So because the water can interact with the solute more, you have a better, or it will dissolve quicker. And with solids, the other thing to do is you increase the temperature, which this is ironically different for a gas, which today is Thursday. So at some point next week, we'll probably be able to talk about gases quickly. Um, there's like, it's chapter 14. Really, if you get one formula, it's okay. There's a couple that kind of build up to it. Um, but a gas, if you increase the temperature, it actually decreases solubility. And in chemistry 12, there's a whole unit on solubility, equilibrium, and different things. So how much can dissolve? As we talked about, if it's water and an ionic compound, you have the water molecules surrounding each ion. So depending on what the solute is, um, you can occupy all of the water. There's not enough space around to get anything else in. So you get kind of an equilibrium where stuff is dissolving and turning back to a solid. So it's kind of like, you'll see these next year, equilibrium. It's going from a solid to aqueous, just as fast as it's going from aqueous to a solid. Nothing else is being dissolved. Nothing is, you can see, it's actually still goes. So terms that you'll see with solubility. Solubility is the maximum amount of something that will dissolve at a given temperature. And you can find all sorts of tables that will give you, well, 63.8 grams of this can dissolve in a liter of water at 25 degrees Celsius. Why does it have to have the temperature with it? Because if you increase the temperature, you'll get more in. Um, so this is a measured quantity. A saturated solution is a relative. These two are relative. Well, I guess technically these three. Because a saturated solution of one thing could have a really, really high concentration or solubility, but a saturated solution of something else could have a ridiculously low concentration. So a saturated solution has the most that can be dissolved. So you can make a saturated solution of salt and water. You basically get a big pail of water and you keep stirring it, you add salt, and eventually you're going to keep adding salt and stuff will stop dissolving. So when you get to that point where no matter how you stir, you can't dissolve anything, that solution is said to be saturated. An unsaturated solution is any point up to that. So if you have that giant bucket of water and you've put in all sorts of salt and you've got the solid sitting on the bottom, because solubility depends on temperature, if you put that pot on a stove, um, more will start to dissolve. And you get what's called a supersaturated solution and then after you cool it, you have more than you physically should be able to because of that kind of nature of temperature affecting solubility. So, so those are linked. And then we have these two. Immiscible is the one that most people recognize quick. Oil and water, you can't put them together. Miscible means two liquids dissolve in each other. This is an old, I remember first seeing this in junior high. If you take 50 milliliters of ethanol and 50 milliliters of water, you add those two together, you get about 97 milliliters of solution because they're miscible because you still have the same quantities if you weighed everything, but because they dissolve in each other, you actually get less. The smaller alcohols, methanol, well, ethanol, rubbing alcohol, isopropyl alcohol to a point will do the same thing. Uh, what affects solubility, and this is what I mentioned, as temperature goes up, solubility goes up usually. For gas, as temperature goes up, solubility goes down. Because as you heat a gas, it starts to move more freely and will end up, it's like boils off quicker. So that's kind of about solubility. Measuring solutions, so concentration. pH of water is kind of a concentration. It's a relative scale. Well, it's a logarithmic scale of concentration of the H plus ion. Um, and it's a measurement. This is a quantity, and it depends on what you're looking at. A concentrated solution has a relatively large amount of solute, a dilute solution. These are different technically from saturated and unsaturated because you can have a solution that has a really high concentration that isn't saturated, which means it's fundamentally unsaturated. You can have a very dilute solution because of what you're talking about that is saturated. So they're terms that going further, it's you have to pay attention to them. So in units, sometimes you'll get grams per liter, grams per milliliter, grams per 100 milliliter, um, percent, weight per volume. So this is really These are both grams or milliliters. This is one that is a little bit more common because any alcoholic beverage is measured, the percent is the percent volume per volume of ethanol in that particular solution. You'll see other ones sometimes, parts per million. Um, I just know that's micrograms per milliliter. You can scale that up to milligrams, I think milligrams per liter. That's a thing you'll see with water levels. There's so many parts per million of lead in water, copper in water, or whatever, or bacteria. You can get smaller. You can get parts per billion, which some things that are even more toxic. This would be micrograms per liter or milligrams per 1,000 liters, I think. So these are ridiculously tiny concentrations. Like you're talking about a drop of food coloring in the Civic Center pool would be somewhere on the order of parts per million, parts per billion. But there are instruments that can measure these. Um, I did, we like doing parts per million is relatively straightforward. We did, I think, one lab in university where we actually measured parts per billion. It was a fairly high parts per billion, but it still technically is parts per billion. So these are ones that you'll see like in kind of everyday life. Um, but in chemistry, when we're talking about reactions, things don't happen in grams. They happen in moles. So we're more concerned with the concentration that we refer to as molar, which I think is on another page. I left this in here. How would you make a liter of a 6% solution of methanol? Um, so 6%, a lot of these concentration equals amount per, well, if I know this is 6%, I know that's a liter. 6% as a decimal. Well, if I multiply by a liter, you need which is 60 milliliters. If you dissolve 60 milliliters in a liter, you will get a 6% solution. 60 milliliters divided by 1,000 milliliters times 100. Um, because these are mainly percentages, I generally, oh, well, that is, we can talk about that one later. But they're all in a weight or mass or some sort of thing like that. But we're concerned about molarity or molar concentration. And generally speaking, we have the formula. Concentration is N over V, where this is molar concentration. This is moles volume in liters. The unit for this is the moles per liter, which is a ratio which we abbreviate as capital M. So I'm going to do, I think, well, it's 9:18. I don't want to be here too long. What is the molarity of a solution that has 2 moles of sodium chloride in 4.0 liters? I do this. Concentration, I don't know. Moles. Volume, 4.0 liters. C equals N over V. Now, whether you go down or over is somewhat moot. The moles is 2 moles, 4.0 liters. Moles divided by, so this 2 divided by 4, 0.50. I got in the habit in university of just doing that. If we use the capital M, those are equivalent answers. So that's kind of the straightforward, simple one. What we can play with units. Well, that's milliliters. Well, we don't measure moles, we measure mass. So kind of the other thing is how many moles we can go to grams. So what is the molarity of a solution that has concentration? I don't know. Moles equals volume equals 250 milliliters. Our defined thing says the volume must be in liters. So everything that we do in chemistry is generally done in liters. So we need to convert that to liters by milliliters divided by liters, or 1,000 equals liters. 0.250 liters. Concentration is mass per volume. Now I know 3 moles, 0.250 liters, 12 moles per liter. So those are kind of the straightforward types. We can mathematically rearrange, like we have 3 variables. If I want to find moles, I multiply volume and volume cancel. Volume, so number of moles is your concentration times your volume. How many moles of salt is required to make 6 liters of a 0.75 moles per liter solution? So this time I know concentration, I don't know moles, and I know the volume is 6.0 liters. Well, I can rearrange that. Some people will just remember all 3. If you want volume, you have to divide that by concentration. Moles equals concentration times volume equals. This is, if you do this, it's a little bit harder to see. 3/4 of 6. It's too early in the morning. 3/6 are 18 divided by 4 is 4.5. Trust yourself. 4.5 moles. Now I'm just going to look at this kind of over here. Moles equals 0.75 moles, because this is a ratio per liters, times 6.0 liters. This is where looking at units, I've got liters in the denominator, liters in the numerator. This is why that comes out as moles, because those cancel out. All right, we'll do one more. How many grams of calcium chloride, we'll stop after this one, are needed to make 625 milliliters? So some people like to just 625. Well, that's 0.625 liters. Concentration is 2 molar. Well, there's our formula. How many grams? If I find grams, can we convert grams to moles? Yeah. This is where moles equals concentration times volume. And just for space, concentration is 2 moles per liter. Liters, 0.625 is 5/8, but I don't want to do that. 2 times 0.625. So we need so we've found this out. If you do that on a test or whatever, you're going to get half of your value, if not slightly more, because you've done the molar, the concentration part, but the question asks for grams. Well, now we need to go back to, I can't remember what chapter, 9, 10, 11, somewhere in there. Moles of calcium chloride. I want grams. Calcium is 40.08 plus 35.45. 110.98. That many grams in 1 mole. We do our mole conversion. I'm going to multiply that by 139 grams of calcium chloride would be required to make 625 milliliters of a 2.0 moles per liter solution. Sounds like 600 milliliters is, well, don't judge. This is 710, so a little bit less than that. That much water, if you dissolve 139 grams of calcium chloride in that, shake it up, you're going to have a 2 mole per liter solution. So that's kind of the basics of concentration. We'll do a little bit more. What is the concentration if you're given a mass? There is some questions on here, but these we'll all deal with because these, if you wanted to practice number 5, number 6, number 7, mass, you could start a question like that. But technically, you're all capable of figuring out the rest. But if you want to practice a couple things, those questions in there, I will save this and put everything up here in a minute. But that's where we'll stop today. We'll kind of look at a couple of those. We'll talk about concentration of ions, which is relatively straightforward. The concept of dilutions is important, and stoichiometry of solutions. Hopefully that sounds okay, and hopefully it doesn't get too hot in Sussex today. It's nice and foggy. I can barely see the telephone pole across the road out the window, so come on, fog, stick around. But that's where we'll stop for today. Sound okay? Oh, Sarah's out. Well, I'll see Sarah in a minute. Bye. See you in a bit.